Hello, everyone. We are officially started, but people are still joining at a fairly high rate. So I think that before we officially get started, we're going to just give people a few more minutes to show up. We have 163 people signed up, which is, I guess I was thinking that we would get 30. So we'll see how everything goes. There are some empty spots in the schedule. If any of you are doing numerical relativity research and would like to give a lightning talk of about 15 minutes or less, there is a link in the chat. If you want to go there and sign up, that would be great. The amount of time we give everybody will depend on how many actually do that. So please take a look and think about what you might want to contribute. Okay. There seems to be a pause in people coming in, so I'm guessing that we have fairly close to the number of people we're going to have. I'm going to be probably sending you all emails every day, letting you know about schedule changes. We've already had a speaker move from Wednesday to Thursday that I just put on our internal schedule. That doesn't show up on the website or anything. Everything that we're going to present today will be recorded, similar to some other Einstein Toolkit workshops. I'm hoping to make some of the links of previous ones available to you later. I'm not sure how many people here have a familiarity with numerical relativity. This workshop was not intended to introduce the subject of numerical relativity to novices. However, we hope that you will still find things of interest here if that describes you. Some of my initial talks will be about this project called the Einstein Toolkit and have a little more focus on the software side of it. So we hope that even if you have difficulty with the concepts of numerical relativity, which is a very difficult discipline, you will still find that of interest. Another schedule change that you should be aware of is that the talks by myself, the tutorial by myself and the talk by Eric Schneider on Carpet X have been reversed. So I will begin the tutorial for approximately 9:30. And Eric Schneider, then we'll have our social time from 10:30 to 11. And Eric Schneider will take over talking after 11. Every day we plan to finish up by 12. If you are having trouble with the tutorials, however, you might want to hang around and we can try to help you. Again, I was imagining we had a smaller number of participants than we actually do, so getting everybody help with the tutorials, if you're stuck on anything, might be a little harder than we anticipated, and we ask for your patience. Okay, so hi, Eric.
Good morning, Steve. Good morning, everybody. Good to see you.
I have switched our talks as you requested.
Yes, I saw that. I'm ready for 11 or 12 my time.
Great, thanks. All right, so I'm going to start with the first presentation about the intro to the Einstein Toolkit. Hold on. So this is a deck of slides that has been prepared by many people that have worked on the Einstein Toolkit before, and people who currently work on it. It's sort of a mishmash of things. So in the beginning, and by the beginning, I mean 1.3 billion years ago, two black holes, each about 30 solar masses, collided. They released 3 solar masses worth of mass energy as gravitational waves. Earth was in the Proterozoic era, and life consisted of eukaryotes, including multicellular life forms. 541 million years ago, the Phanerozoic eon begins, and complex life, including vertebrates, appear. 1 million years ago, Neanderthals appear. 200,000 years ago, anatomically modern humans appear. In 1687, Newton publishes Principia Mathematica. In 1905, Einstein publishes his paper on special relativity. In 1915, Einstein publishes his papers on general relativity. In 1916, Schwarzschild publishes the Schwarzschild black hole solution. In 1936, Einstein correctly describes gravitational waves after going back and forth for a while on whether they exist or not. In 1956, Felix Pirani eliminates coordinate confusion and describes gravitational waves using curvature. In 1963, Kerr publishes the Kerr black hole solution, which is a rotating black hole. In 1994, the head-on collision of 2 black holes was simulated on a computer, as well as distorted single black holes. In 1995, distorted rotating black hole solutions were simulated by me. In 1997, Cactus was created by Paul Walker and Joanne Masseau. It remains as one of the best completely open source collaborative frameworks for studying numerical relativity. And that is the framework on which the Einstein Toolkit is built. And you'll be learning more about that through the week. In 2005, Franz Praetorius published his results on evolving black hole spacetimes, which was the first multi-orbit in-spirals of black holes. In 2012, the Einstein Toolkit that we know and love was created. In 2015, LIGO detected gravitational waves from those 2 black holes that collided 1.3 billion years ago. The event was called GW 150914. Oh man, look at those cavemen go. You know, one of the things I miss about these Zoom presentations is any kind of audience feedback. You can't hear people laugh or people clap, or I guess you can still clap. There's a clap button, but in any event. So what is the Einstein Toolkit? You could do a thumbs up. What is the Einstein Toolkit? It is a collection of scientific software components and tools to simulate and analyze general relativistic astrophysical systems, such as black holes and neutron stars and the like. It is freely available from einsteintoolkit.org. It is supported by a large number of grants, and that list looks out of date. I thought I updated that one. Anyway, we recently obtained a new grant, a new 4-year grant to continue developing the Einstein Toolkit. It is a state-of-the-art set of tools for numerical relativity, and it is completely open source. There are over 259 members of the Einstein Toolkit at 172 sites in 39 countries. More than, those are all slightly old numbers. There have been more than 200 publications regarding the Einstein Toolkit. It's regularly and rigorously tested. User support is available through various channels. We have a Monday morning call. We have a mailing list, and so on. At the bottom, You see pictures of some of the biggest contributors to the Einstein Toolkit. There's myself, Peter Diener, Roland Haas, Helvi Witek, Zachary Etienne, Bruno, I can't say his last name, and Eric Schneider. Giacomassi, I think. I'm probably mangling that. The science done using the Einstein Toolkit is vast. We do black hole mergers, neutron star mergers, study supernovae, look at accretion disks, boson stars, hairy black holes, cosmic censorship. It's a community effort. So prior to the development of Cactus, the numerical relativity community was like, I think, many scientific communities at the time. It was fragmented. Every code was written by a hero graduate student who did all the work themselves. Nobody really built on anything. The purpose of the Einstein Toolkit was to come up with a way that we could work together, that we could put code, each person could contribute code from a variety of institutions and have something work. And why do we need that? Well, because it seemed inefficient for everybody to keep rewriting the same things over and over again, especially when so much of it, so much of the effort is not really new science. It's just, learning to program maybe. So there are a number of computational challenges which we face. In the beginning, computation was fairly straightforward. We had a device like this. But nowadays, we have a number of different types of devices to work on. We've got the iCore 9 processors, for example, which many people are familiar with. We've got the NVIDIA processors. We've got, which are GPU accelerator processors. We've got GPUs by AMD. We now have the ARM processors coming into play with the newest top 500 machine, Fugaku. And that's a picture of the A64FX chip used by Fugaku. So the other thing that's happened during the years, I mean, it used to be the case that you write your Fortran program, you run it on one processor and you're done. But over the time that the Einstein Toolkit and Cactus have been around, computation has become more diverse. You have to take care of more and more issues. This is a picture of the Fugaku machine, the newest top 500 machine in Japan. And whenever I see it, whenever I see this picture, I think of this picture, the Borg. Time for the laugh track. Okay. So the computational challenges for the Einstein Toolkit are to simulate cutting-edge science using the latest numerical methods and making use of the latest hardware. So and the latest use of hardware requires making use of cache, of vector instructions, of scaling to many cores, of scaling to many nodes. So many cores would be many processes within one computer, and nodes would be multiple computers. Algorithms, code speedups historically and in almost all disciplines are driven more by algorithms than improvement in hardware. And so to keep track of all these things is becoming too much for any one person. While at the time Cactus was created, people could still write hero codes on their own and expect to make use of all the hardware that was available. In the years since then, that really isn't possible anymore. You really need to understand a lot more about computer science just to get the code right. So, as I say, the efficient use of all hardware is complex and tedious, and you require experts from a number of different disciplines. You have to get good data layouts, and you have to figure out what the right APIs are that will make sense for people. You need to ensure correctness. You need to have good modularization of on a number of different levels and understanding of advanced programming concepts to really do these things. You need to design and implement, you need design and implementation needs to be carefully thought out in order to ensure extensibility and portability. And these are some of the areas where Cactus has really done quite an amazing job. I mean, it's not, part of it was the basic design of how the interfaces inside Cactus fit together that has worked well for a lot of people. But it's been there's the community effort at maintaining them, extending them over the years, and keeping everything tested and running correctly. This kind of effort has really paid off. Okay, so just to give you one small taste of one of the issues that one deals with when doing computations across multiple computers is the concept of ghost zones. So one of the things everybody has to figure out if they're going to write a code that's going to run on a high performance machine is how to decompose into domains with ghost zones. So that means that when you're doing a computation, you have different parts of the computation happening on different grids on different machines. So the black holes might only be colliding on a handful of the processors, while many of the other processors might be simulating regions of the space-time where gravitational waves are propagating away. And some of the regions might be different resolutions and so on. But the way this works, the way you're able to do computations across multiple machines is by using what are called ghost zones. So typically, any computation at any point on the grid of a numerical computation takes into account data from neighboring points. And you need a way to exchange the data between different processors to make this happen. So that's what ghost zones are for. Between each step, we copy the data from ghost zones from one machine to the other, and then we're able to do the pointwise calculations to carry everything one step forward. And this requires a certain amount of synchronization across all processors. And while this description is, I think, fairly straightforward, and among the numerical and computational issues, it's one of the simpler ones, even this is going to take anyone a fair amount of time to do from scratch by themselves. The Einstein Toolkit and Cactus do this automatically for you and hide this complexity from you, allowing you to focus on the science you want to develop and not all these numerical details. So when you decompose your domains for these ghost zones, this is a two-dimensional picture of the way you might slice up your grids. You have to imagine, of course, that for a black hole or collision or a neutron star simulation or whatever, you're going to have a three-dimensional space that you're going to be dividing up into 8 pieces. And it's actually even more complex than that. Your grids don't always line up in those boxes as you've seen them. They can be different resolutions, they can overlap, they can have slightly different geometries. And this is a typical simulation for a black hole collision with multi-block and refinement, showing the different grids, the way they relate to each other. And you can see where the black holes would go. It would go in those 2 highest resolution blocks in the center. So we talked about computational methods and computational challenges. So the question is how to make use of the latest hardware. And this challenge has largely been addressed by generating code. So instead of programming directly in C++ or Fortran, one programs in a higher level language such as Mathematica or Python. And then from that, code is generated. And this is one of the ways that we are able to make use of the vector units. So while many codes only need to put -03 or something on their compilation command line to make use of vector units, the Einstein Toolkit has to compile very complex expressions. Right-hand sides for numerical relativity codes could take hundreds of pages to write out. And the vectorization routines on most compilers simply fail. So we have to write our own code to get the vector units to work. Scaling to many cores is usually handled by OpenMP, which is not a technology that we invented, of course. This is a markup language that one uses with compilers to specify which loops can be parallelized and in what way. Scaling to many nodes requires a couple of different technologies: MPI, Carpet, and Carpet X. Now, Carpet and Carpet X are what are called thorns, or modules of the Einstein Toolkit. They are, in particular, what are called driver thorns, and they are the principal tools used to hide the complexity of programming in MPI, of decomposing in ghost zones, of adaptive mesh refinement, and other things that are required to scale to many nodes. And so you see Carpet and Carpet X mentioned again here under algorithms. Adaptive mesh refinement or AMR is a way of conducting a simulation simultaneously at multiple different resolutions, where interesting science gets higher resolution and the boring areas where not much is happening get lower resolution. And what Cactus, the Einstein Toolkit, Carpet, and Carpet X enable you to do is they enable you to focus on just how do you update data in one region of space-time to the next, right, without worrying about the rest of this complexity. Another item on this list here is MOL, method of lines, and that is the time stepping algorithm used. There are multiple time stepping algorithms used in numerical science, and one of the nice things about the abstractions provided by Cactus is it lets you not worry about those. You can just sort of choose one. You can say, I want Runge-Kutta 4, and the system will provide it for you. That doesn't intertwine itself with the code that you're writing. Making use of the GPUs. As of yet, the Einstein Toolkit and Cactus have not really made use of GPUs in any kind of production way. There have been a number of efforts to make use of GPUs within the framework, but they've generally stayed within the academic realm, the theoretical realm. And what about FPGAs, floating field programmable gate arrays? This is a technology that exists on some machines. It hasn't caught on widely enough that we have seriously addressed it. But the point is that the latest hardware is an evolving target. We're going to continue to we're going to continue to have new kinds of hardware to make use of, and we need a framework. We need modularizations and abstractions to help us do that, because not everybody can learn how to do all these things. In fact, very few people can learn how to do all of them. You can usually find someone who will do some set of them. And so qubits would be quantum computing, and I don't know that we will ever do that with the Einstein Toolkit, but it is not impossible that someday that's a thing that we will have to make use of. Okay, so you've seen some of the highest and most difficult challenges, but there are more mundane challenges that everybody has to deal with when writing a computational code. There is efficient I/O, input-output. Seymour Cray once said that a supercomputer is a device which takes a computationally bound code and turns it into an I/O bound code. And there's a lot of truth to that statement, even today. The newest cluster being built at NCSA, the Delta machine, has been redesigning the I/O at an operating system level to eliminate some of the challenges that many codes have in this area. So I/O is a very important consideration if you want your code to run fast. HDF5 is a portable binary format, and you want your code to be able to use this for a number of reasons. One of the things that's possible with Cactus is checkpoint and restart different number of processes on different machines. That's an important thing. And there I mentioned it as a bullet point. Parameter parsing. This is possibly one of the more mundane considerations that you could have for writing any scientific code. You have some kind of parameter file which tells you, where to place the black holes, what masses they have, what spins they have, and so on. But this is nevertheless a piece of code that has to be written, and it doesn't make sense for there to be hundreds and hundreds of different parameter parsers for the same types of code. So it makes sense to have a framework like Cactus, like the Einstein Toolkit, just take some of these more mundane tasks out of the scientist's hands. There's also the challenge of visualization. Creating lots of data is great. You can learn a lot of things, but until you visualize it, you often don't know what you have. And so visualization is an important part of the science, and the modules that are developed and the tools that are developed to visualize code can be as important as the code to generate the data. Steering. This has been de-emphasized over in recent years in the Einstein Toolkit, but one of the things that you can potentially do is you can start a simulation, you can monitor it live as it's running, and then decide to change some parameter during the evolution of your code to make it do something different or better. Okay, so those are some of the more so you've now seen some of the more complex challenges and some of the more mundane challenges, and hopefully I've shown you why something like the Einstein Toolkit is needed, and what it can do for you, how it can make your life easier if you want to do physics, if you want to do astrophysics, numerical relativity. Okay, so collaborative challenges. People don't always get along. We start with some kind of problem. We have a bunch of different groups that are working on similar things. We have a bunch of different machines in a bunch of different locations. And rather than these all being silos, these should be a community. And we have a number of different tools by which that community can keep in contact. These are some of the tools that we've used historically. Not all of them are as important as they once were. But in any event, we have a number of software tools that we use to hold our family together. So we have different groups that work together, and there are problems. There is competition between them. Sometimes different groups want to get all the credit for themselves, and sometimes they want to share it, or some combination. And we need to make sure that both are possible. So the Einstein Toolkit is open source. It is a base layer, and any group can take that code and they can build a module on top of it and do their science. And they don't have to share that code that they build on top of the Einstein Toolkit, although that we hope that they do. And what many people do when they create a new module for the Einstein Toolkit is they publish a paper or two with a scientific result, and then subsequent to that, they make their code available to the rest of the community. And we have a process in the Einstein Toolkit by which we vet code and accept it into the framework. We need standards. We need different ways. We need common APIs and ways of managing code and data in order to communicate and cooperate. And HDF5, of course, is one of those great ways of doing that, because it is a portable binary format for data. We need a number of tools to share. People program in different languages, and the Einstein Toolkit and Cactus tries to be language agnostic between C++ and Fortran. There have been discussions about including other languages into the mix over time, but as far as module writing, those two have been the mainstays so far. We can run the Einstein Toolkit on a number of different platforms. You can You know, it's one of the things that makes the code more robust is we run it on many different machines and you see different problems with different compilers on different platforms. The other nice thing is that we're able to distribute credit. So after you share your code, right, other people can, you can get credit. Other people can either cite the papers that you write, or we have a DOI that can be cited for the Einstein Toolkit. And if you contribute, if you become part of this community and you contribute to the Einstein Toolkit, you can be added to the document identifier, the DOI that describes the people who have contributed to the Einstein Toolkit. And so people are able to all, you know, work on the same kinds of problems with the same kind of efficiencies, and everybody can get some credit. So here is a smattering of different countries and research groups, both in the USA and in other countries that work on the Einstein Toolkit. We have Louisiana, Illinois, Virginia, Pennsylvania, and Georgia and California in the USA, and other countries include Italy, Spain, Portugal, Canada, and Germany. We are community driven. We are a core computational tool for general relativity. It's a general purpose tool. We actually have multiple different codes in the Einstein Toolkit. You'll learn more about that later in the week. We have a special code for certain kinds of black hole collisions, and Peter Diener will talk to you about that. We have different components to the Einstein Toolkit that fit together. We have Cactus, we have the simulation factory, we have Crank. Cactus is the core. The sim factory is some Python code that's used for building and running simulations. Crank, as we've talked about before, is a Mathematica code for code generator. NeRPi Plus is a Python-based code generator. We have a number of science modules. There are guiding principles to our community. We are open, we are community driven. We believe in good interfaces, the separation of physics from computational infrastructure. We have code reviews with varying levels of strictness. So the Einstein Toolkit is and has been growing ever since it was created in 1997. It started with Cactus. We had growing numbers of applications and both computational infrastructure and science modules. A basic picture of the modules. Here's the thing that we're trying to solve: G equal T. That would be Einstein's equations for general relativity. We describe the space-time curvature. There's some constants, and there's the matter. And the matter can include hydrodynamics, electromagnetism, particle radiation. We have ADM base as one of the basic modules. The TMU new base, so that's the curvature and the matter pieces. We have MLBSSN, which will evolve them. We have hydrobase, which provides some basic infrastructure for doing hydrodynamics. And then GR Hydro, which makes use of those modules. We have modules for initial data and analysis. And we have thorns such as Illinois GRMHD and Lean BSSN MAL to evolve spacetimes. And so, as I say, these are our guiding principles. We're open, community driven. Separation of physics and infrastructure, computational infrastructure. We have stable interfaces allowing extensions. We simplify our usage when possible. Students need to know a lot about physics, and it takes time for them to develop that. The Einstein Toolkit cannot give you that. However, open codes make it easier to concentrate on those things rather than figuring out all of computer science in addition to figuring out relativity. You can cite the Einstein Toolkit in the following way. It's not required that you do so, but it's polite and we ask you to. Our vision for the future is to remain cutting edge. We have a new driver thorn, which should say carpet X. For some reason, I didn't write that. We have a new declarative synchronization mechanism, pre-sync, which allows us to update our ghost zones in a more coherent way. New spherical coordinates thorn is coming from RIT soon. We have the new Python code generator that you've heard about, NERPy+. We have recent thorns, Praca, Lean, and Giraffe, which you will probably hear more about during the week. So the point is, we're constantly developing new science thorns, new computational infrastructure, and generally carrying the discipline forward. So the Einstein Toolkit is this. It's used in much high-end research. And here is an updated list of the various grants that have been used to support it. All right, I'm a little over time, but since I'm in charge of the schedule, I guess I can forgive myself. So are there any questions? If there are, I suggest we use the chat to obtain them. Let me pull up the chat.
Steve, what
Yes.
sometimes works is people raising their hands in the chat, and then you can let the people speak and present the question.
Yes, I can do that too. I just can't see everybody in the chat because there's so many.
I think whoever raises their hand floats to the top of the list of participants.
I see. All right, so if anybody wants to raise their hand, yes, Nilay.
Hello, sir. Am I audible?
Go ahead.
Yes, sir. So I had just a doubt, like to use the toolkit and the information which it provides. So like, does it require like a threshold level of knowledge? Like if you have some undergraduate and you have not much done work in astrophysics, so is there any like certain boundaries?
Yeah, so you're going to, okay, so it's going to take some work to learn how to use the toolkit. It's going to take some work to learn how to understand the science that's being produced. We believe that the Einstein Toolkit makes that process a little easy. I mean, we believe it makes it easier, but it's still significant work. You're still going to you're probably going to have to contact our user community and interact with us to fully understand everything that you're doing, but we're here for you. Any other questions?
Can you please raise your hand again if you have a follow-up to the question? I believe I may have accidentally muted you. Also, for future participants, when you raise your hand, if you could turn your camera on for the recording's sake, I would appreciate it.
Any other questions? Okay, I don't see any.